Don't you hate being an early adopter? Hello everyone and welcome to another video on our own devices. I'm Jean Messier and today we are having a look at yet another aircraft reflector gun sight. This is the sighting head of a Type A-4 gun bomb rocket sight installed in a number of 1950s, 1960s American jet fighters and fighter bombers, including the North American F-86 Sabre and F-100 Super Sabre, the Republic F-84 Thunderjet, and the Douglas A-4 Skyhawk. Now I know many of you are eagerly awaiting part 4 of my series on reflector gun sights, and yes, it is coming. But I recently came across this in a friend's collection and knew I just had to cover it, so consider this part 2.5 of the series. Now, I've already covered the principles of reflector, gyro, and radar gun sights in part 1 and 2 of my series, but very briefly, calculating the correct lead or deflection needed to hit a crossing target requires two key pieces of information: the turning rate of the attacking aircraft and the range to the target. Gun sights like these use gyroscopes to measure the former and a radar to measure the latter, and use this data to adjust the aiming reticle. But if you want to learn all the gritty details, make sure you watch those videos first, link in the description. In this video, I will be focusing more on the specific implementation of those principles in this particular gun sight. Right, so let's dive right in. So the A-4 sight was an upgraded version of the earlier A-1CM gun sight, the main difference being the method of projecting the reticle. In the A-1CM, two separate bulbs were used to project the central pip and outer ring, while the A-4 uses a single bulb and an outer reticle ring composed of diamond-shaped pips like on the original British World War II gyro gun sight we looked at in part 2 of my series. There are also various differences in the layout of various components and the sensitivity of the system to vibration, a problem which plagued the gun sight throughout its service life. The first F-86A Sabres that arrived in Korea in 1950 were equipped with the World War II era Mark 18 gyro gun sight, but these were found to be too slow and cumbersome for use in high-speed jet combat against opponents like the Soviet MiG-15. So starting in 1951, they were replaced by the A-1CM, while after the Korean War, this itself was replaced by the more sophisticated A-4. Later versions of the Sabre, like the F-86D, K, and L Sabre Dog, integrated the A-4 sight into the MG-4 fire control system, which used a more sophisticated AN/APG-36 radar and scope to allow for all-weather and night interception. Now, according to the data plate, this particular unit was built by the AC Sparkplug division of General Motors of Flint, Michigan, specifically in their Milwaukee, Wisconsin plant. This stencil bears the date March 1st, 1954, which may be the date of manufacture. However, the letters MFP here likely stand for moisture and fungus proofing, a special waterproof coating applied to optics to protect them in tropical environments. So March 1st, 1954 may simply be the date that this coating was applied or that the unit was overhauled or reconditioned. I really don't know. But if any of you know any more, please let me know in the comments and I will be sure to add that extra information to the description of this video. Anyway, despite this being a whole lot larger and heavier than the other gun sights we've looked at, this is still only the sighting head and formed part of a much larger system. This was mounted behind the aircraft's instrument panel and was connected to 5 other major modules: the radar, the computer, the amplifier, the range servo, and the rocket setting unit. Now, as this sighting head doesn't have any sort of beam splitter or viewing screen, I initially assumed that this projected the reticle image directly onto the aircraft's windscreen, but as it turns out, the beam splitter is simply missing from this particular example. Now, if we turn this around, you can see that we have quite a few external controls. Now, as I mentioned before, this is designed to be used with a radar to measure the range to the target. In the F-86, this would have been the AN/APG-30, mounted behind a small radome above the engine intake. However, for the system to work, the pilot still needed to know the approximate size of the target they were attacking, and they would manually enter this information by turning this big knob at the front, calibrated from 600 to 6,000 feet in 100-foot increments. This was used together with the manual ranging control, which we'll talk about in a minute, such that when the target just filled the reticle ring, it was at the proper range per the harmonization of the aircraft's weapons, a technique known as stadiometric ranging. And speaking of harmonization, the unit could be bore-sighted to the aircraft's guns or rockets by removing these two access panels, elevation on the top, windage or deflection on the front. And this access panel allows you to adjust what is known as the bomb stop, the function of which we will look at in a minute. On the left of the unit, we have a dial beneath a small glass window that continuously displays the range to the target, as well as a red light that indicates whether the radar is locked onto the target. This is another minor difference between the A-1CM and the A-4. On the former, this light was mounted separately on the aircraft instrument panel. and the plug beside the light is to connect equipment for ground testing the site without having to activate all the aircraft systems. Meanwhile, on the right, we have a lever that allows the pilot to cage and uncage the reticle position motors, that is, allow them to move freely or lock them rigidly in place. This is often done with gyroscopes to protect them from damage during particularly violent maneuvers. And interestingly, we have a big stencil on both sides of the site warning that this side must not face up, likely because this could cause the motors to drift out of their design parameters. But once again, I'm not quite sure about this, so if you know any more, please let me know in the comments and I will add it to the description of this video. Now, there is also an electrical caging button mounted on the aircraft throttle, which, when depressed, caged the gyros in the Gunsight computer to stabilize the reticle image just before starting an attack. At the last moment, the pilot released the button, uncaging the gyros and allowing the sight to operate normally as he went in for the final attack. And by the way, pressing that button automatically reset the sight to gun mode. Now, there were a number of peripheral controls not mounted to the sight head itself. These included the gun safety switch, which when set to camera and radar mode supplied electrical power to the sight, ranging radar, and gun camera. The A-4 is designed to be used with either the Type N9 or AN6 gun camera, and to learn more about these fascinating devices, please check out my previous video on the GSAP, link in the description. When the switch was set to gun mode, power was supplied to the weapon solenoids, allowing them to be fired when the trigger on the control column was pressed. There was also the dimmer rheostat to vary the brightness of the reticle, the filament switch which selected between the primary and secondary filament on the reticle illumination bulb, which, by the way, can be accessed and replaced by turning and pulling out this knob on the front of the sight head. Normally, multiple filament bulbs are used to vary brightness without having to use a rheostat, but in this case it was simply for redundancy. If one of the two filaments burnt out, the pilot simply switched to the other. Next, we have the sight selector panel, of which two types could be installed, variable or fixed. This incorporated a number of different controls, the first being the sight function selector, which allowed the pilot to select between gun, bomb, and rocket mode. In rocket mode, the reticle depressed to compensate for the greater ballistic drop of the particular rocket being fired. For example, the 5-inch high-velocity aircraft rocket, or H-4, on earlier F-86 variants, and the 2.75-inch folding fin aircraft rocket, or FFAR, on the F-86D Sabre dog, which in turn was selected by the rocket setting unit on the center pedestal beneath the main instrument panel. And to learn more about the history of unguided aircraft rockets, please check out my video on the CRV-7, link in the description. Each of the rocket setting lever positions also had two detents that further adjusted the reticle based on dive angle, N or normal for 0 to 40 degrees, and S or steep for 40 to 60 degrees. In the variable version of the sight selector panel, the depression of the sight in mils could be manually calibrated during test firing runs, and the appropriate settings marked on movable index markers on the dial, allowing the pilot to dial in the system according to their particular attack technique. Now, switching the system to bomb mode depressed the reticle image by 10 degrees and engaged a very clever mechanism in the Gunsight computer, which worked on the fact that the slant range from the aircraft to its ground target can be related to the vertical line of sight rate of the aircraft. Now, unfortunately, I don't have an example of the Gunsight computer to show you, nor have I been able to track down any detailed diagrams of it. However, from what I've been able to determine, the A-4 system differed from earlier gyro and radar gun sights in that the two gyroscopes for measuring lateral and vertical turning rate were located not in the sighting head, but in the computer, which controlled the position of the reticle indirectly via electrical servo motors. Each of these gyros, in turn, was integrated into a larger mechanism incorporating a fluid damper, an accelerometer weight for measuring and compensating for gravity and ballistic drop, and pneumatic bellows for compensating for altitude and airspeed. Now, getting back to the bomb aiming mechanism, placing the system in bomb mode engaged something called the super elevation assembly into the elevation gyro, locking it against the bomb stop I mentioned before. Now, when the pilot aligned the depressed reticle with the target, he entered a wide, slightly spiral outside loop, placing the aircraft in a negative G condition. As the spiral got progressively tighter, the G-forces steadily increased until, at a point determined by the computer to correspond to the tangent of the correct bomb trajectory, the negative Gs caused the super elevation assembly to disengage, releasing the elevation gyro and sending a signal to the servos on the hard points to release the bomb. It also briefly caused the ring on the reticle to wink out, signaling to the pilot that the bombs had been released. However, automatic bomb release could not be used for weapons weighing over 500 pounds because these tended to strike the airframe under negative G conditions. Now, if I ever get my hands on one of these Gunsight computers, I'll definitely cover it in its own video or produce an extended version of this one. Moving on with our peripheral controls, we have the manual ranging control, which is mounted to the throttle handle and designed to be used when the ranging radar fails or becomes unreliable due to interference from terrain. Twisting the handle adjusts the diameter of the reticle such that if the proper target wingspan is entered and the reticle just brackets the target, it is in proper firing range. Next, we have the radar target selector button, which allows the pilot to select which target the ranging radar locks onto. Pushing the button causes the radar to reject its current target and scan for another target farther out. The pilot can keep pressing the button and rejecting targets until the radar reaches its maximum sweep range, whereupon it recycles to its minimum range. A related control is the radar range sweep rheostat, which allows the pilot to vary the sweep range of the radar to prevent it from locking onto ground objects when flying at low altitude. And finally, there is the bomb target wind control, which compensates for wind during ground attack and has two settings, upwind and downwind. Right, so with all that out of the way, let's finally open this up and have a look at the internal components. And by the way, if you ever get your hands on one of these and try to disassemble it, the aforementioned MFP coating glues the seams together, so after you undo all the screws, you have to pry the two halves apart with a crowbar. Right, so on the left-hand side of the unit, we have two reticle position control motors, which are connected via this linkage to this pivoting mirror. Normally the mirror and motors are free to move, but if we engage the caging lever, we can see how it locks them in place. As mentioned before, these are controlled by the gyros in the computer, which also contain electromagnets which adjust the stiffness or sensitivity depending on a number of factors, including the range of the target or type of weapon being fired. For example, the closer the target and the greater the projectile velocity, the shorter the travel time and thus the less deflection is needed. More current will thus be fed into the electromagnets, making the gyroscope stiffer and less sensitive. We can also see how the motor linkage engages with the bomb stop, whose position can be adjusted through the aforementioned access panel. Moving over to the right of the unit, the light from the lamp travels up this tube through a double diaphragm assembly similar to the one in the British gyro gun sights we looked at in previous videos, which generates the reticle image. This image is reflected off this mirror, collimated by this lens, then reflected off the gyro-controlled mirror up into the beam splitter and back into the pilot's eyes. If I place a flashlight underneath the light tube, we can see the reticle ring made up of diamond-shaped pips. We also have a pair of servo motors to rotate the two reticle diaphragms, adjusting them for target wingspan and range. These in turn are connected to the ranging radar, manual ranging control on the throttle, and the manual range adjustment lever. The latter is not connected rigidly, but via this camming mechanism. The smaller the target wingspan, the more restricted the maximum diameter of the reticle ring, meaning it could not expand past point-blank range. That is, the maximum range at which no deflection is needed to score a hit. And that, dear viewers, is a brief breakdown of the A-4 gunsight system. But one question remains: did it actually work? Well, newer pilots in Korea using the A1CM sight for the first time tended to really like it, while veteran pilots accustomed to the older Mark 18 gyro sight found the A1CM unnecessarily complicated and cumbersome to use. The system also suffered from many early teething problems, particularly the tendency of airframe and gun vibration to jitter the reticle into an unusable blur. Jolts and vibration from rough airfields as well as heat and moisture also rapidly damaged the system's delicate components. Manufacturers attempted to alleviate these issues by adding rubber dampers and the electrical caging switch I mentioned earlier, but problems persisted until the end of the war. Pilots also found the requirement to smoothly track targets for the sight to work properly inconvenient under actual combat conditions, while the 1,500-yard maximum range on the sight caused problems at closer ranges since the system took a long time to compute a ballistic solution. For this reason, a device called the Jenkins range limiter was introduced, which prevented the radar range signal from exceeding the value selected by the pilot. Yet despite these many problems, the A1CM was extremely sophisticated for its time and gave American pilots over Korea an enormous tactical advantage, allowing them to achieve kill ratios of between 5-to-1 and 10-to-1, depending on which source you read. And the later A4 system corrected many of the problems that plagued the earlier units. Anyway, that's all I have for you today. Thank you so much for watching, and I'll see you next time in another video where we'll look at yet more gun sights and other fascinating devices just like this one. Until then, I'm Jean Messier from Our Own Devices. Have a great day.